All right, so this is actually problem 6.3 in your book. So I didn't do a very good job of drawing it, but it's a beam with a pin at A and a roller at B, and this is point C right here, kind of in the mid-span. So it's 6 feet, 9, 9, and 9 feet, respectively. So part A wants the vertical reaction at B. Now, at this point in the course, if I had assigned you problem 6.3, we would have just had either the tabular method or the function method. But now we have the Euler-Breslau. So that's what I'm going to do. I'm going to use Euler-Breslau. So if we want, I'll draw it right here. So I'm looking for, excuse me, A was vertical reaction at B, so this will be BY. Let's see what we got. Yes?
Can you clarify, now that we know Euler-Breslau, is there any reason to use that old stuff?
I would say you do the way that gets you where you need to go. I think Euler-Breslau gets you there way faster. Yes. So if you understand it, you should just do it. Yeah, because that's, we can draw shear influence lines and reaction influence lines. They just kind of appear. There's really no calculation. There's no statics involved. The moment one, you have to kind of take pause and do a little bit of work. But they're way faster than having to develop all those equations and then plot them. So I would say, yeah. So let's do that. Let's review that part. So I'm going to go ahead and make some marks where things are going to happen, possibly. So remember what we do is we're going to remove B's ability to have a vertical force, and then we're going to apply a vertical force there. So what is this point B going to do when I push up on it? Is it going to go up or down? Up. It's going to go up. So it's going to really seesaw around A. So you're going to end up with something that looks like, oop, I left the line off the very edge of the beam. So you're going to end up with something that looks like that, because I pushed it up here at B. Now the easiest point to find is, well, what is the reaction BY when my unit load is moving, and what's it going to be when it's right above B? It's going to be 1. So I know that this value right here is going to be 1. So this is 18 feet, another 9 feet, and this is 6 feet. So 1 is to 8. This is similar triangle. So 1 height here is to 18 as what is to 27? 1.5, right? Every time you go 18 feet over, you go up 1. So I went over another 9 feet. That's half. I go up a half. So this would be 1.5. No? You guys following that? You got 43? 4/3?
Oh, well, it's actually 6 feet.
No, 6 feet's over here.
Oh, both are 6.
Did I draw it wrong?
I thought both are 6 feet.
No, it says 6, 9, 9, 9, 9.
Oh. Huh. That explains it then. Okay.
Now this is going to be different, right? Because this is what? 1 to 18 is what to 6? It should be a third.
Yeah. Okay.
So see there, we've drawn the influence line, and there's really there's some mental calculations in doing but I really just established the slope of the line and then just projected that slope. Now, would I ask you to do this? Is this the end of the problem in the exam? No. Because then on top of this, you would then apply dead loads, live loads, maybe moving loads. That's more likely what you're going to see. But if you don't do this right, well then you're kaput. Okay, so the second one, or not the second one, part B wants the moment at, I'm sorry, I'm reading the wrong one. No, it wants the moment at C. So let's draw that one. So again, I'll make a template. Our ordinate value is the moment at C. There's C. So again, I'll project these lines down where the supports and in the beam are, and then I'm going to also add C because that's pretty important. So how are we going to do for moment? Remember what we do is we go back up here to the point we're interested in, which is the moment at C, and we're going to take the beam's ability to have moment capacity. So basically put a hinge there, and then apply positive moment. So C is going to move up, and as it moves up, you can see it will seesaw over A, and then also seesaw over B. So I'll just pick some value here at C, and then make sure it passes through 0 at B and through 0 at A. I probably chose a little too high a value because I went off my graph.
Why don't we move it up?
Because we apply positive moment to it.
Oh, okay. Yeah. Gotcha.
That would cause the sections to rotate up. So now we got a lot of things going on here. So you can pick any position you want. Now remember, this is the moment at C, and this is a plot of the moving load. So where do you want to do it? I don't really know what the best place to do it is. If we wanted that value right there, that means the unit load would be right here on the edge, and we're still cutting it at C to find the internal moment. You can do it any way you like. But the one I always like to do is the value right over the point. So what that means is I'm looking at a structure that looks like this. So I'm going to have my reaction at A, my reaction at B, and then at C, that's where my unit load is. And if we look at all the distances, this will be 6, 9, 9, 9. And I'm trying to find the moment there for this position. So I'm going to cut it here and probably look at, well, not probably, either the left side or the right side. I don't see any advantage. I'll just go to the left. So that means I'll need my AY reaction for this. Then I'll cut the structure and find the moment. So how do I find the AY reaction for that? I'll sum moments at B. And summing moments at B, my unit load creates a positive moment. So that'll be 1 times a moment arm of 9. And then AY creates negative moment at a moment arm of 18.
Could we have found BY using our original diagram that we drew?
We could have.
Yeah, okay.
You would have had to then go up here and interpret that value. So that's when the unit load is at C. What's BY equal to? It's equal to that right there, which would be 1/2. And we're going to find out that BY and AY both are 1/2. So yeah, you could have. So in this case, we found that AY is 1/2. So now we'll cut the structure, and we're looking at the left side. We've got our newfound reaction of 1/2, and we're looking here for the moment at C. And this is 9 feet, and this is 6 feet. So what's the moment at C? Well, we'll just sum moments at the cut. So the internal moment is positive. The reaction creates negative moments, so it'll be minus 1/2 times 9. So it looks like the moment at C is 9/2 feet. So that means this value right here is 9/2. So what's this value right here? Well, this 9/2 is to this distance, which is 9, as this is to this distance, which is also 9. So that makes this negative 9/2. Now here's a little different because this is 9, 9, 9, 6. So 9/2 is to 9 as what is to 6? Well, 6 is 2/3 of 9, so I need 2/3 of that. The 2 cancels, I get 9/3. It ends up being -3. So the moment influence line takes a little bit longer to construct. The last one is the shear just to the right of support A. This was a little tricky, actually. So let's draw our template. So this is shear at A, but it says just to the right. So I'll put a positive there, meaning to the right of A. And I'm gonna draw it a little bit differently to help you see it. So let's do this. Let me redraw the structure here, and I'm going to put our little shearless connection just to the right of A. Let you kind of see it. This is where Mueller-Breslau gets a little. It works, but you have to think about it for a second. So just to the right. In fact, I'm going to overemphasize the just to the right part. Okay? There's A, and then we get back over here to B. Now remember, when we do that, we come along and we apply positive shear to both sides. Now just imagine this little moment arm here, this little lever being really, 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 really small. Like super small. As small as you can imagine. So how is this side going to behave when you push down on that really, really, really super small edge?
It's barely going to behave at all.
What's going to go up or down?
It's
going to go down. Barely. And this side's going to shoot up. So you're going to get some. So you're going to get something that maybe looks something like this. It's not going to go down on the right-hand side because it's super, 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 super tiny.
Okay.
Now, on the right-hand side, what's going to happen when I push up? It's going to go up. I tried to draw these with the same slope, but I'm not successful. You know what this change right here is? 1. So what's this value right there? 1. What's this value over here? Well, 1 is to 18 as what is to 9? 1/2. Now, what about this guy? What do I do with that? Well, you have to realize that these are the same slope. So again, 1 is to 18 as what is to 6? 1/3. So that's the tricky part. This is the part that's a little confusing, I think, when you try to find Mueller-Breslau. Now you might notice in most of our work we didn't do any of these just to the right or just to the left because they're kind of a little tricky. So I would not bet the house, but I'd bet a large sum that it won't appear in problem set 4. That's in my eye. Sorry. What time is it? Oh, it's out of time. What else do you want to do?
Sheer force and benefit.
Oh, that takes 25 minutes.
But we have 15. Yeah.
We can talk about it. How about that?
Yeah, we can talk about it.
Let's talk about it, because sometimes it can be tricky depending on the problem. I could pick one in the book that is doable in 10 minutes. But I could also pick one that looks almost the same that's not doable in 10 minutes. So maybe we should talk about the strategy. You have to go all the way back to chapter 4 to see those. And you might remember, too, that shear force and bending... Oh, I should stop this yapping. Okay, goodbye.